The next linear model we're going to consider comes from the computation of half-life. Half-life is the ability to measure the stability of a radioactive substance. Another way of thinking of half-life is the time it takes for half of the atoms associated with the substance, the object, to disintegrate or transmute to another element. So the example we're going to do for half-life will involve plutonium-239. So suppose that you had a breeder reactor. And in the reactor that you've lost a certain percentage of the original plutonium. So suppose that you've lost 0.043%, which is a very small percentage. Suppose you've lost that much of an initial amount. And we'll say the initial amount you had was a 0. Suppose you've lost a very small percentage of the plutonium 239 after, let's say, 15 years. That'll be useful information. And the goal is that we want to know, the question at hand is, what is the half-life? We'll abbreviate it HL. What's the half-life of plutonium 239, assuming that it disintegrates proportional to the amount that's remaining. So again, we're looking at that very similar to the growth model we have for bacteria. We're going to look at this relationship again, and perhaps the constant will be slightly different this time, but so far the model looks pretty much the same. That you'll have an initial amount, and it's going to be changing according to a differential equation, very simple one of that linear form, for which you already know the solution again. This time the initial amount's a 0, so the solution will be of this form, and of course the goal is to figure out what K is. But the difference between the bacterial growth is this is not growth, this is disintegration. So this is a reduction from what you started with. In fact, we know for a fact that after 15 years, we have reduced the amount of plutonium to 0.9957 times A0. That's just removing the 0.043% that you've lost. So that's another way of writing that condition. Now, using that information, that would suggest then, push this up, that 0.9939 there, 57 A0 then, again, is the amount we have after 15 years. But using the formula that we have now for the disintegration or decay of the element, this must be A0 times E to the K when T is 15. Again, because that's the form of the solution we already know. Now, of course, the A0 elements go out, and the goal here is to find the particular K that describes this decay, and it will turn out to be simply 1 over 15, just solving the simple equation using natural logs, times the natural log of 0.99957. And because that natural log is less than 1, you can immediately tell that's going to be a negative number. You're going to get negative 0.00040 followed by 2867. So then the model of the half-life, in this case, turns out to be A of T is your initial amount, then multiplied e to the negative 0. Again, followed by 40,000,2867 T. So you're definitely going to decrease through time because of that negative exponent. There won't be growth in this case. So the goal was to figure out exactly how long it takes to get half of the plutonium in the reactor, or disintegrates to half of it. So what we want to know is for what T, and this will be in years, Will A of t be equal to half of what you started with? So that's what it means to determine the half-life of the element. So again, we would set 1/2 A0 equal to the model of decay that we have, which is A0 times e to the negative 0.402867 t, and solve for t. Of course, we use natural logs. What you're going to get is the natural log of 1/2 is going to be equal to the natural log. Of course, you're taking both sides, e to the negative 0.402867 t, and you should be able to realize, of course, that's the same thing as the natural log of 2 to the minus 1 power. This will be the same thing as negative 0.00002867 t, but this is just going to be negative natural log of 2. You can pull that exponent out. And we're going to see that time is going to be positive value, which is very good. It's consistent with what we expect in time. So the time it's going to take to disintegrate half to the original amount of plutonium that you had is going to be the natural log of 2 divided by this small number, 2867. Okay. And that, if you calculate that, or if you use a calculator real quickly, that's going to be about 24,180 years, which is a long time to get down to half of the amount of plutonium. And that's what typically happens in these types, in uranium and plutonium decay cycles. They're very, very long decay cycles. So that's an illustration of another very simple linear model, but this time the difference is that the K, the proportionally constant, K was negative in this case. It was not positive, so it was decay. The last thing we're going to look at, very similar to this because it's very interesting, another really interesting application that involves this type of growth or decay, is carbon dating. So we're going to look at our third application for linear models in terms of carbon dating. So with carbon dating, it's understood that radioisotope carbon-14 is usually, it's produced in the atmosphere, and it's really readily occurring, and it's produced by a cosmic radiation on nitrogen. So it's produced because of cosmic radiation coming from the outer atmosphere, sun, for example, cosmic radiation acting on nitrogen-14. Okay, but when an organism dies, typically what's going to happen is it stops absorbing carbon-14, and you can use the fact that the amount of carbon-14 generally in the atmosphere remains constant, so you can estimate the organism's age. So let's do that. Here's an example. Okay, it's kind of an interesting model. That let's suppose that you had a fossil, and it contains, let's say 0.1%, very small, 0.1% of its original amount carbon-14. So you've determined that it's been dead for a long time. How long has it been dead? Because you've got a trace of carbon-14 left. So again, the question is, how old is the fossil? Again, using our very simple linear differential equation, we can answer this question, again, based on the rate of change of amounts, like decay. So the constant times how much you have, A, with some initial amount, A0. Right? And again, as we've done the previous two models, you already know the form of the solution. With that initial condition, the solution would be A0 times e to the kt power. We already know that. We need to find k. So to find k, we need to use the information that we have. One information that we have is a known half-life. So there is a known half-life for carbon-14. Okay, so that's not given in the example because it's already known. So carbon dating is done with this information already known. It is known for carbon-14 that the half-life, the time that it takes to get half of the value, is about 5,730 years. Okay, so that's the half-life. Right? That was actually discovered by Willard Libby at the University of Chicago, approximately circa around 1950. They were able to come up with the half-life of carbon-14. So using that information, then you would know that 1/2 A0 would have to be the amount of carbon-14 after 5,730 years. Set that equal to our model equation, A0 e to the k, evaluated at time 7,330, and then solve for k. That's going to pretty much come up with k. You can show that that will give you k is going to be minus natural log of 2 divided by 5,730. So that's approximately going to be equal to negative 0.00122097. So it's similar to what we just did with half-life because the carbon-14 is going to disintegrate. So the model for carbon dating then is that the amount of carbon-14 left after T years is your initial amount multiplied by E times negative 0.3 zeros after the decimal, 12097 T. So there's your model that you can now use for doing carbon dating. All you need to do is come up with the amount. How much trace of carbon-14 do you have? So our particular problem, we know that there is 0.1%. That could be written as 0.001 of the original amount. That's the amount that we've been able to determine is in the sample. If we set that equal to the model and then solve for t, we'll figure out how old it is. So we're looking for figuring out the time that matches this value. So we'll set this equal to A of t. I'll write it this way, A of t, which is equal to A0 e to the minus 0.000122097 t, and solve for t. It'll tell you how old the fossil is. Again, the A0 components go out, and then you take natural logs. You're going to get the natural log of 0.001. It's going to be negative 0.000122097 t, and then again dividing out, what you're going to have is that t, because that natural log is going to be negative as well. And we could think of the fact that that is going to be 10 to the minus 3, so we can rewrite this as the natural log of 1,000 divided by that small quantity, 0.000122097. Again, because looking at the fact that this will become the same thing as 10 to the minus 3, so that'll be negative ln of 10 to the 3. There's your 10 to the 3. The negatives will cancel out, and we'll get this. And the approximate age of the fossil is 57,100 years. So with that trace of carbon-14, you can see how old it is. The smaller the trace, obviously, the older the fossil will be. So that's another really nice illustration, very close to the half-life application. And again, we're looking at K, where K in this case is much less than 0, it's a negative number, you're going to reduce the amount of carbon, but you can use the linear differential equation here, figure out a particular amount that you have of carbon-14, solve this equation for time, and you'll know exactly how old it is based on the half-life of carbon-14.